So there are three different types of proof that you need to know of. Now, most of the proofs that you will be asked will be of the third type, but you still need to know of the first two. Annoyingly, the first two are actually the easier ones. The first type of proof that you need to know is proof by exhaustion. Proof by exhaustion is when there is a set number of inputs, so you can actually just prove them individually, as there isn't actually too many examples that you actually need to prove. So this is an example that I've actually taken straight from the spec, that is their example of proof by exhaustion. So what we can see is that there is a set number of values of p, and it's prime numbers that are bigger than 3 but less than 25, and then all we just need to do is find the values of p and then individually sub them into this equation, and then prove that they are all a multiple of 12, and I would say this is worth about 4 marks, this question. So the first thing that you need to do is actually define what the values of p actually are, and we use this using this fact here, that p is a prime number such that p is bigger than 3 but it's less than 25. So what I'm going to do is, as we're using this fact here, I'm going to quickly write that down in order to show, in order to make the proof clear that that's where we're getting that from. So I'm going to say, as p is a prime number such that 3 is less than p but is less than 25, it is going to, p is going to equal, it's not going to be equal to 3 because this isn't the equals inequality sign, so it's not going to be equal to 3. P is going to be equal to 5, 7, 11, 13, 17, 19, and 23. And now we just need to sub all of these values individually into this equation in order to do it. So first of all, we're going to do, when p is equal to 5, it's going to be 5 minus 1 times 5 plus 1. We need to write this method out in order, because we need to show full steps, so we need to show us subbing 5 into the value of p. We need to show us subbing all the values for the values of p, and then this is going to be equal to, if you put this into a calculator, this is equal to 24. Now we need to show that this is a multiple of 12. This looks quite simple for 24, but you'll find that there's bigger values as you get on, so you need to find a way to prove it. And the way you can just prove it is just by saying that 24 divided by 12 is equal to 2, and that's a good enough explanation in order to say that 24 is a multiple of 12. We can just leave it like that, and then we just need to prove it for all the other values. So when p is equal to 7, it's going to be 7 minus 1 times 7 plus 1, which, if you put that into a calculator, is equal to 48. And then we can do 48 divided by 12, and that is equal to 4. So that's really long-winded, I know, but now we've actually proved it all here. So now we just need to write a statement at the end. Remember, for all the proofs, you need to write a statement at the end. And as I said, this statement is just therefore, and then we're just going to repeat the proof. So the statement is just going to be therefore. Remember, these 3 dots represent therefore. Therefore, given that p is a prime number such that 3 is less than p and p is less than 25, p minus 1, p plus 1 is a multiple of 12. And then that is the answer, and that is how you write the entire full proof like that, with that statement at the end where literally you were just saying, basically you're just saying that you've done the proof. Therefore, we've just kind of got rid of the prove that, and we've just written that is literally all you need to do for the final statement. And then that's the question. And if you get that in an exam, you'll be so happy, because that is worth 4 marks, and that is 4 incredible. It's very long-winded, I must admit, especially this kind of whole part here. But once you do it and you're just subbing in values, you'll be able to just get 4 very easy marks secured. So there's another type of proof by exhaustion question where you need to consider all positive integer values, but you class them into sets using algebraic expressions. So here's a question like this where we need to prove that all fourth powers are either a multiple of 8 or one more than a multiple of 8. So as I said, you need to class all positive integer values into sets, and the number of sets depends on the number of sets of different outputs you can get. The number of sets of inputs you sub in is equal to the number of sets of outputs you could get out. And in this question there are 2 sets of outputs that we could get out. They could either be a multiple of 8 or they could be one more than a multiple of 8. So as there are 2 sets of outputs, there are 2 sets of inputs that we need to sub in as well. So therefore we need to class all positive integer values into 2 sets. So what do we actually mean by this? Well, we need to class all positive integer values into 2 equal sets. And the way we can do this is just classing them into even and odd. Another way of saying this is a multiple of 2 or one more than a multiple of 2, and we'll see in a sec why we could describe it like that suitably. All numbers are either even or odd. So it separates all positive integers nicely if we separate them into even and odd numbers, and we can represent this algebraically. Even numbers can be represented by 2n, where n is any positive integer. We talked about this at the start in the tips. N is any positive integer, and it doesn't matter what positive integer it is, 2n will always be even as we're timesing it by 2, so it will become a multiple of 2 by definition. And likewise, for odd numbers, we can represent odd numbers by 2n plus 1. 2n plus 1 will always be odd as we're just adding 1 to 2n, which is an even number. And we can prove these individually, and we will find one of these inputs will give one of these outputs, and the other input will give the other output. For this question, we need to consider all positive integer values, as we need to consider all fourth power, so therefore we need to consider all positive integer values that give these. And as all positive integer values are either even or odd, if we individually prove this is true, this proof up here, if we prove it's individually true for even and odd numbers, we prove it for all positive integers. So sometimes there might be more than 2 outputs, so I must admit I've stolen this question from the textbook. It's question 4 in 7e. I'm not going to answer it, I just want an example where there's 3 outputs. In this question, it's either a multiple of 9, one more than a multiple of 9, or one less than a multiple of 9. There are 3 outputs, so therefore we need 3 inputs. So we need to class all positive integers into 3 sets, and we can do this because all numbers will either be a multiple of 3, one more than a multiple of 3, or one less than a multiple of 3. And we can represent these algebraically. A multiple of 3 will be represented by 3n, because no matter what positive integer value n is, timesing it by 3 will always make 3n a multiple of 3. And therefore, one more than a multiple of 3 can be represented by 3n plus 1, and 1 less than a multiple of 3 can be represented by 3n minus 1. And what you can actually end up doing is you can put any number of sets using this multiple rule. You can do it for 4 sets, for example, as well, if you needed to, by doing a multiple of 4, 1 less than a multiple of 4, 1 more than a multiple of 4, and 2 more than a multiple of 4. Really quick, sorry, this is actually another question I've used from the book. This is question 24a in the mix exercise 7. Sometimes you'll need to use the idea of n, any positive integer, in other circumstances without it being about outputs. So in this example, it wants you to prove that the difference of two squares of two consecutive even numbers is always divisible by 4. Well, what you can do is you can use n in order to represent two consecutive even numbers. Two consecutive even numbers, so the first even number can be 2n, because remember an even number is 2n, and then we need to find the consecutive even number, aka we need to find the even number after that, and that is just going to be 2n plus 2. That is going to be the even number directly after it, and then you can sub these values in for the two consecutive even numbers for the problem. Okay, so this is the question right from the start, and we're just going to prove it now using the thing that we said before. So as we know that there are two outputs, a multiple of 8 or one more than a multiple of 8, we said that we're going to use two inputs to define all the numbers, or all the positive integers more precisely, and this is going to be even, which is equal to 2n, and odd, which is equal to 2n plus 1. And remember, even and odd class all positive integers. And the way we solve this is that we're going to prove these individually as either being one of these each, and therefore as we proved it for even or odd, as all numbers are even or odd, we've proved it for all numbers. Okay, so first of all, let's start with even numbers. So remember, we're going to be clear. We need to use words and sentences to be clear. So for even numbers, and this is defined by 2n algebraically, we know that the fourth power of an even number is going to be either a multiple of 8 or one more than a multiple of 8. We don't know which one, but it's going to be one of them. So the way we're going to do this is we are going to do 2n to the power of 4, as we're doing fourth powers, and this is equivalent to 16n to the power of 4. And therefore we need to prove that this is either a multiple of 8 or one more than a multiple of 8. Well, we can prove that this is a multiple of 8 by, and this is quite a useful tip for proofs in general, is that we can factorise 8 out of this to do 8 2n to the power of 4. And then as we're timesing 2n to the power of 4 by 8, therefore this is going to be a multiple of 8, as we're timesing it by 8, and therefore if you times something by 8, it's obviously going to become a multiple of 8. So therefore we can say that 8 2n to the power of 4 is a multiple of 8. And therefore, we have proved for even numbers that it is true that it's going to be a multiple of 8. Again, because we times it by 8, we times 2n to the power of 4 by 8. So therefore, this whole thing is by definition going to become a multiple of 8. So we've proved it for even numbers. Now we just need to prove it for odd numbers. So for odd numbers, which is divided by 2n plus 1, it is going to be the other output. It's not going to be the multiple of 8, because we've already proved that's the case for even, so it's not going to be the multiple of 8. We know that for odd numbers, it is definitely going to be one more than a multiple of 8, so we need to prove it for this. So what we're going to do is we're going to do 2n plus 1 to the power of 4, and this is going to be equal to 2n plus 1, 2n plus 1, 2n plus 1, 2n plus 1. And then this is going to be equal to, well, if we expand these brackets separately, and we need to prove that this is going to be one more than a multiple of 8. Well, the way we can do this is we can do a method similar to before, where because we've got this plus 1 on the end, everything here, all the coefficients here, are a multiple of 8. So therefore we can factorise 8 out of this first part here to do 8 2n to the power of 4 plus 4n to the power of 3 plus 3n squared plus n, and this is going to be plus 1. And then because this here is a multiple of 8, again because we're timesing this by 8, so then by definition it's going to be a multiple of 8. If we plus 1 to it, it is going to become 1 more than a multiple of 8. So therefore 8, 2n to the power of 4 plus 4n cubed plus 3n squared plus n plus 1 is going to be 1 more than a multiple of 8, as this here is a multiple of 8 because we're timesing it by 8, and then we're just plussing 1 on the end to make it 1 more than the multiple of 8. And therefore we need to write a sentence in order to explain why this proves for all fourth powers. As all numbers, or more specifically, as all positive integers are either even or odd, as all positive integers are either even or odd, we have proved it separately for even and odd, and therefore as all positive integers are even or odd, we proved it for the whole thing, and then we just write, remember we write the statement at the end, basically just saying that we've done the proof. We always need to write the statement, so the statement is just going to be, as all positive integers are either even or odd, therefore all fourth powers are either a multiple of 8 or 1 more than a multiple of 8. And therefore that is the full proof, and if you write that all down you will get the marks for this question. Now the reason this is because all numbers are either even or odd, and as we proved it individually for even and odd, all positive integers are either even or odd, so therefore we've proven it individually for all positive integers and therefore all fourth powers. And the main thing to take from these questions though is that the main way to approach them is that the amount of outputs that there are, in this case there is 2, they can either be a multiple of 8 or 1 more than a multiple of 8. That's the set of values that the outputs could be in. That is the amount of the set of inputs, the number of set of inputs that you need to do. So in this case it is 2. The second type of proof is proof by counter example. This is basically when you actually need to disprove something. You need to disprove a statement, and you need to disprove it by giving an example simply for when it's not true. That's all you need to do. You just need to disprove a statement by just giving one example for when it's not true, and you only need to give one example. So this is actually the example that is mentioned on the spec. I've just taken this example straight from the spec. This is the one they use for proof by counter example. And we need to show that the statement n squared minus n plus 1 is a prime number for all values of n is untrue. Now kind of the theme with proof by counter example questions is that some values will actually work when you sub it in, but all we just need to do is just find one value for which it won't. So all we just need to do is just sub in values into your calculator until you just find one value that disproves it. And I just quickly found that 5, when you sub it in, isn't a prime number and it disproves it. So the way we'd write this in the proof, remember we need to be clear, is we're going to say when n is equal to 5, and then we're going to sub, remember we need to do the full steps, we're going to sub 5 in as n. It's going to be 5 squared minus 5 plus 1, if you put this into a calculator, is equal to 21. We don't need to prove that 21 is not a prime number. That's kind of just like a given. 21, which is not a prime number. So, and then we just need to do the statement at the end. Remember, for the statement we just repeat whatever the question is. So I'm just going to repeat this part here. So therefore, remember these 3 dots represent therefore. Therefore, the statement n squared minus n plus 1 is a prime number for all values of n is untrue. And that is the full proof, and that will give you the marks. Usually these questions won't be worth a lot of marks, so they'll probably worth 2 marks or something like that. Really quick, for some questions there can be less examples, so when you can disprove it, and most inputs will actually work. For these, you just need to take a step back quickly and think about it logically. So for example, for this question, we need to disprove that all values of x, for all values of x and y, x plus y squared is bigger than or equal to x squared plus y squared. When you first start plugging in values into your calculator, or positive values, you actually find that it does actually work. Even when you plug in 0 as both x and y, because of the equals inequality, it does actually work as well. All you just need to quickly do is just take a quick step back, and eventually when you just look at it, when you consider negative values as well, you'll be able to see that when you make x equal to 1 and y equal to -1, something like that, on this side they're going to cancel out and make 0, but on this side, because a minus, when you square a minus number, it becomes a positive number, this is not going to cancel out and it's going to be 2. So the way you would write this proof is, so when x is equal to 1 and y is equal to -1, well, for this inequality, well, this part over here, it's going to be 1 plus -1 squared, which is equal to 0 squared, which is just equal to 0. And then on this side over here, it's going to be 1 squared plus -1 squared, which is equal to 1 plus 1, which is equal to 2. And 2 is bigger than 0, so therefore you've disproved that this is the case. So for all these questions, you just need to take a step back quickly and think about it logically, and kind of think outside the box a tiny bit, and think about, so in this example, you think about negative numbers and positive values kind of cancelling out like this. And then remember, you just need to write a statement as well. So I'm just going to write therefore, and it's a bit difficult to kind of write this particular one kind of like it. Just kind of like just think about something in your head. The statement just needs to make sense. It doesn't need to be a specific thing. So I'm just going to say therefore the statement for all values of x and y, x plus y squared is bigger than or equal to x squared plus y squared is untrue, and that would get you the marks. Really quick, when I was just making this video, I actually wrote this as the statement at the end, and when I was actually looking back on this, I realised that this is actually a really bad statement, because what I'm actually implying is for all the values of x and y, it is always untrue. That is actually kind of what this statement actually looks like. So just be slightly careful with your statement and make sure that it does actually make sense.